A scatter plot basically just looks like a discrete graph. There's a bunch of dots everywhere. And there's three different types of associations that we can have. Okay, now a scatter plot just shows the relationship between an independent variable and a dependent variable. We could have a positive association going up, negative association going down, or no association, just there's no relationship at all, right? So a scatter plot, we're not going to go too in depth on it just because it doesn't necessarily matter too much in terms of our test. But, oh, you guys got it? Okay. So the positive one's going up, negative one's going down, right? Pretty obvious. Now, it's not all in a straight line, but it's closely clustered together points. So a positive association just means as the independent variable x increases, then the dependent variable y increases as well. So if one of them's going up, the other one's going up. A great example of two data points that would have a positive association are age and height. If I went to each of you, well, that wouldn't make sense. You're all the same age. If I went out in the world and found 100 people and recorded all their ages and all of their heights, say I ask a bunch of little kids, some teenagers, some adults, some older people, what relationship do you think age and height are going to have? As age goes up, what do you think happens to height? Height probably goes up as well, right? Babies are a lot smaller than all of you. Right, Anthony? So that's what a positive association looks like. Both variables are going up. When one goes up, the other one goes up. Can anyone think of another example that might have a positive association? Anything in the world? Talk about it with your group for 60 seconds. See if you can figure something out. Something that has a positive association. Two variables. Take a minute. Figure it out. Who do you have for math this year? Really? No, I don't think so. That's good, right? No. Oh, that's right. That's right. This is the class you're in right now. In what context? Oh, yeah, like a runner? Yeah. The longer time goes by, the more distance they run. Yeah, absolutely. That's a great example. Did you think of that? Yeah. That's awesome. Yeah, this is math 1. All right, let's come back together. Anthony had a great example of a positive association. Anthony, what was yours?
Distance and time.
Distance and time, right? In the context of...
So like the longer you run, the more distance. The longer you run, the more distance you run.
Absolutely. It could go for runners. It could go for driving a car. The longer that you're driving, the further your miles go. Both variables are increasing, right, Anthony? Do you have another one?
Yeah, I have another one.
Perfect.
So it's like, you can use a bread as an example, because like, if you put it in an oven or heat it up, the hotter it gets, the more bigger it gets.
Oh. So, time versus size? Yeah, that works. That's an interesting one. I wouldn't have thought of that, but you're right. Bread rises when it goes in the oven. So the overall, we could say like maybe the volume of the bread versus the time. As the time goes on, the volume increases. Absolutely. That's a great one. Anyone else come up with anything? Nobody else came up with anything? Okay, that's all right. Negative association is just the opposite, right? As the independent variable increases, the dependent variable this time around decreases. What's a good negative association? As x increases, y decreases. As x increases, y decreases. Anthony.
When you get older, don't you get smaller and shorter?
Yeah, I mean, yeah. Are you talking about the age and height one? Yeah, you do shrink up a little bit as you get older, but we're not worrying about that. That it would kind of be like we'll actually talk about what type of graph that would look like in a little bit, but yes, good point. In general, though, the older you get, the taller you get, up to a certain point, right? Can anyone think of a negative association? Yeah, Judah? A basketball game? Okay, what are the two variables?
Like the time goes down and there's a score goes in.
Good, I like that one a lot. So, time, you said time, yes, yeah. Time left. So score and time remaining. Absolutely. If I had a graph where the independent variable was the score, and over here is the time remaining, let's say it's a 12-minute quarter, right? Right? After 0 points have been scored at the very beginning of the quarter, how much time is left? 12 minutes. Right? And as we go down, right, this is going to get down and down and down. Naturally, the score is going to go over and over and over. The score can't, they can't take points away. So eventually we'll see points going down negatively like this. As the time goes on, the score increases. That's a great example. Thank you, Judah. Absolutely. Anyone have another example maybe for negative association? I always like to think in terms of students, like something you can all relate to is hours spent studying versus, wait, I think that's going to come up in a second. Oh, that's actually the last example. I'm going to hold off on that for a second then. And then no association is easy. There's no noticeable relationship between the two variables. Just looks like a discrete graph. There's no pattern, nothing going on, just points scattered all over the place, right? Now this one's easy. Can anyone think of something that would have no association? I can think of one. How about your height and your GPA? Right? The taller you are, the higher your GPA, right? No. The shorter you are, the lower your GPA? No. There's no relationship between height and GPA, right? Does that kind of make sense? So what's something else that wouldn't have any relationship? This is the easy one. It could literally be anything. Anthony?
Corn and algebra.
Corn and algebra? Corn in what context?
The more corn you
Like the amount of corn eaten? And the amount of algebra,
amount of corn in a corn.
the amount of corn in a corn? Kernels in a corn?
Yeah, kernels.
Versus what about algebra? Okay, I said it could be literally anything. Maybe I lied. Well, corn and algebra. Let me think. We could say like amount. You don't have to write this down, okay? But you can. Amount of corn eaten and algebra problems solved. Right? So like the problems solve themselves the more corn you eat. Very creative thinking. I like that, Anthony. We made it work. It does have no correlation.
I mean, the more corn you eat, the less algebra problems you solve because the more corn you eat, you spend more time.
You could be multitasking though. You could be eating corn and solving algebra. You could be doing the algebra in your head. No one ever said you had to write it down. Does that make sense with no association? This thing is pretty self-explanatory. I think we're getting a little off track. That's my bad. So let's take a look down here. This scatter plot shows the relationship between hours spent studying. That's my X. I'm going to write that down here. Hours studied. And the score on the test. Score on the test. I want you now to, with your group or someone next to you, describe the association. Which of the three is it? And what it means in the context of the problem. So write a sentence explaining what this association has to do with the hours studied and the scores on the test. All right? Take like 60 seconds, 90 seconds, something like that. Talk with your group, see if you can figure it out. If something doesn't make sense, what I said doesn't make sense, Ask someone else. See if it makes sense.
Why do you go so far?
Are you doing good at math? Yeah? You got what? That's good. That's awesome. How's applied math? Ken?
I can't get my grade on those.
Wait, who's your applied math teacher?
I don't know. Yeah. Bro. We all look at
Sorry, my bad.
And he keeps being absent, so I would date him.
Oh, that's not good. All right, let's take a look. Who could help me describe this association? What type of association do you see on this scatter plot? Melanie? Positive association. Give me a thumbs up if you agree with Melanie. This is a positive association. Good. How can we tell? Yeah, Alex? The dots are going up. From left to right, we're going up. That means that as my hour... Oh, sorry. Can anyone interpret what that means in the context of this problem? Chloe? The more hours you study, this is true for the most part. The more hours you study, you said what? The higher test score, or the higher, sorry, I can't spell. The higher your test score. Right? Now, when we're describing this association, right, and we're explaining what it means, it's not a 100% true statement necessarily, right? If you take a look, this person right here, I'm going to zoom in. Right, it's not a surefire thing. This person right here studied for 3¼ hours and got an 85%. This person right next to them only studied 3 hours and scored like an 87.5%, right? So there is certain instances where people score it higher when they studied less, but that's the point of this, is we're looking at the overall trend. We can see, hey, this data is definitely trending upwards, meaning on average, the more you study, the higher your score, right? I don't see anyone that studied 0 hours and got 100% on this test, right? I also don't see anyone that studied for over 4 hours that got less than an A, right? So we could say, in general, the more hours you study, the higher your test score. Okay?
But the person that didn't study for 0 hours, somebody at least passed.
They got, oh yeah, this person with 0 hours got 62. Yeah, but in general,
Is this graphic theoretical?
talking about the one that's right above 60.
Is this a theoretical?
Yeah, why? All right, let's get the second page. The biggest.
Be happy when they win.
Oh yeah, always. Haven't been moving on.
Did you see? But look. Bro. Bye, Mr. Church.
Hi guys, thanks for coming by. See you guys later. Yep.
If you run a 5.5, you're faster than me.
So inflation doesn't rate. How? Inflation is faster than rate.
How are you going fast?
Yeah, if the demand for something sophisticated and simple, let's say something like inflation, let's say like
For lunch, he was like, do you want to bring my first fry? I was like, okay, I'll do that when we go home. And then she was like, Kristen hasn't been coming home.
trying to think about the indicator.
Yeah, I'll go home and do her. I can't do that with them, so like, I'm gonna have
So
to do
in
it.
terms of Pokemon cards, right? A negative association has the price increase. The number of sales. If something's getting more expensive, there's gonna be less of us who have access to it. But you're asking right, as demand increases, price increases.
That's not bad.
Anybody not get the second page? Nope? Okay. All right, so we're not going to get too in depth on this stuff. This is. You guys ready? Okay. We're not going to get too in depth on this normal curve, but eventually, hopefully, you guys will take statistics or AP statistics in high school, and this is like the holy grail of statistical analysis, is this idea of a normal curve, okay? So it involves using a histogram. That's why we did our warm-up on a histogram. And there's 3 different types of distributions we can have. Distribution is just like association. Associations with scatter plots, distribution, histograms. Okay, but it's basically the same thing. It just means the shape of the graph. So a normal distribution looks like this. Has anybody ever seen like a graph or a curve like this before?
Yeah.
Yeah? Okay. It's the most common one. There's tons of real life examples as to where we can see normal curves. So basically what a normal distribution shows is a bell curve. It's like a little mountain, a hill, with symmetrical data clustered around the mean. So if I'm looking at this one right here, right, basically it's a histogram like we saw, but this line of best fit kind of goes over the top. That's my bell curve. The mean is going to be right there in the middle. And the cool thing about a normal curve is that the mean, median, and the mode are all the same number. All right, now this is more just general background. We're not going to need to know this for the test or anything like that, but it's good stuff to know. We've talked a little bit about standard deviation, where you square it and square root it and add them and take the mean, that confusing process that we have to know. So where standard deviation really comes into like an applicable way in stats is with normal curves, because in a normal curve, here's the mean, right? This block of data right here, this center block of any normal curve is 68.3% of the data, and that's one standard deviation to the left, one standard deviation to the right. So you see minus one standard deviation, plus one standard deviation. And then 95.5% of the data is within 2 standard deviations from the mean in either direction. And then this third little break here tells me 99.7% of my data falls within 3 standard deviations on either side. Again, what this means is not super important. I just want to make sure you've heard this before so that it sounds familiar in the future, okay? When we talked about standard deviation means what? Does anyone remember? What is it a measure of, standard deviation? Here's our purple page.
A measure of how strong the data is.
Say what, Tyler?
How spread out the data is in relation to the mean of the data set.
Perfect. How spread out the data is in relation to the mean. Well, in a normal curve, my mean is right down the middle. Right? Right down the middle of that curve. That's my mean. Okay? And if I look at this curve, I can assume, without even knowing what's going on with this curve, a lot of the data is clustered around that mean. It's very, very heavily favored in the center, right? That means that our standard deviation would be very, very low. The closer all our data is to the center, the lower our standard deviation is. Okay? Now, normal distribution, like I said, that's one distribution for histograms. The other two look like this. Left skewed means that a majority of the data is on the right side, which can be confusing. and right skewed, which means the majority of the data is on the left side. Okay, this one's also called negatively skewed. Right skewed is also called positively skewed, but we're not going to worry about those. We're just going to worry about left and right. So if I see all my data waving up to the right, it's actually left skewed. Okay, and if I see all my data getting waved up to the left, it's actually right skewed, is what we call that. All right, and if we put those both together, boom, look at that. We get the little normal curve. Okay. So, some real life examples that I was able to procure up and see, just so we could take a look. Thought it would be interesting. I thought it was interesting. Distribution of newborn baby weights. So if you take a look, my x-axis is the weight in pounds, 6.7 pounds all the way up to 8.5, and then the frequency in thousands is my y-axis, right? So what this graph tells me is that the average baby weight is what? What's the mean here? 7.5. I said it was right in the center, right? So the mean here and the median and the mode is 7.5, okay? So that's like the average weight for a newborn baby. Now some babies come out a little bit underweight, right? But it's not as common. And some babies come out a little on the chunky side, which again, there's nothing wrong with that, but it is less common. So we see kind of the extremes really level out, and as we get towards the mean, towards the average weight, we see a lot more data. Give me a thumbs up if you see what I'm talking about with that. Okay. Another one, distribution of male height. Okay, this is a good one. What does it look like the average male height is based on this graph? 69 inches. How tall is that? It's like 5'9", right? Now, of course, there's some gentlemen that are down here in the 5'1" range. It's not as common, right? But there is data that's there, right? And then there's freaks of nature over here in the high range. That's, what would that be? 6'7", yeah, 79 inches, 6'7", right? But that's also very, very uncommon. I think, if I remember, I just heard this statistic recently that was like less than 1% of men in America are over 6'4" or something like that. Like less than 1% are over 6'4". So when you see like a professional basketball player that's like 6'8", that is statistically insane to be that tall. It's very, very, very uncommon. 5'9" though, pretty common. Right? A lot of you will grow up and be 5'9", and that's okay. Right? That's okay to be 5'9". Some of you are 5'9" right now, I think. I don't know what that means. What is that? Oh, 7'4"?
No.
Yeah, 7'4". Pretty rare. Pretty rare. Another one, shoe sizes. What's the average? Well, I think this is for men. Sorry. I didn't realize that we're also male-centric. What's the average male shoe size? 10, right? Anybody wear a size 10 in here?
No, I wear a size.
None of you wear a size 10 shoe, actually?
Oh, I wear a size 10.
This is not a size 10. Close. Anyone wear a size 9.5 then? 9 or 9.5? Okay, what size shoe do you guys wearing? 7s? 6s?
No, they were like size 5.
That's okay.
Who's wearing a size 15? Most people wear 11.
So again, I'm assuming it's for adult men. It's very rare you see an adult man with a size 6 shoe. It's also very rare you see an adult man with a size 15 shoe. Okay? But as we get closer and closer to the mean, we see more and more data piled up in the center, right? ACT scores. This might be something you take in the future, maybe not. But ACT is like a test to get into college. So what's the average ACT score based on this? 21, right? And the ACT, I believe, is out of 36, I want to say. Right? So something to keep in mind, right? This starts out at 13. It doesn't start out at 0. We have to keep in mind that. And it doesn't go all the way up to 36. Right? It goes to 31. So if we had expanded this out like all the way from 0 to 36, we may see something like this where it's a little bit more left skewed, right? If my data is clumping up over on the right, that would be left skewed. But overall, where the majority, 99.7% of the data is, that would be a normal curve with a mean at, what is it, 22? Something like that? 21. 21? Is it 21? Oh yeah, it is. I'm sure. Yeah, 21. Okay, I think there's another one. Oh yeah, NFL player retirement age.
Tom Brady's
Okay. Yeah, sometimes you get your Tom Brady's that play till they're 43 all the way over here. But you get people like, I don't know if you guys know football, but Andrew Luck, who played he was quarterback for the Colts. He was quarterback for like a couple years, and then one day he was super young, like 25, 26, and he just said, yeah, I'm retiring. I'm good off this. And it was wild. He had too many injuries. He went to Stanford. He's like a super smart guy, so he was like, you know what, I can make a lot of money being an engineer and not get my brain bashed in playing football, so I'm going to do that. So that's what happened to Andrew Luck. But the average retirement age is like around 33. So, I mean, this works for basketball too, right? The fact that LeBron James is playing basketball at what, 40, 41? Crazy. Statistical anomaly, right? Most decent players are washed by 33, like Klay Thompson, right? Here's a great example in real life. Where's this at? At the gym. Take a look. What do you notice about the wear and tear on these plates? There's a lot of it. Where's most of the wear and tear at? 40, 45 in the center, right? So the average weight, because this the metal wears down because you put the little key in it to lock the weights. You guys know what I'm talking about? Yeah. Right? So you see, there's not many people just getting on the machine to do 5 and 10. There's some, but not as much. There's also not a whole lot of people out here pulling 130, 125, right? It's just not as common. But this is a real life, like unintentional example of a normal curve. Where, yeah, the mean I would say is like around 40, 45. And we fan out our data, and it kind of just shrinks out on both sides as it goes around. Anytime I think about like normal curve statistics stuff, I always think about this picture because it's just so cool. It's, no one tried to do this. It just happened, right? And the more data you get, the better of a normal curve that you see. Now on the opposite side of that, some skewed data. This is a left skewed data, right? This is the age at death for Australian men. Okay, you guys see that? Why is this one not a normal curve? It's more to the right. Why is it more to the right?
Because more people will die older.
As they get older, right? It's a lot more common for an older person to die than a younger person. For the most part, right? Based on this graph, at least in Australia, you're statistically at a higher risk of dying at 0 years old than you are at 45, 50 years old. Okay, because of complications due to birth, all that kinds of stuff, right? So yeah, you see a big spike right here at 0, but then after that, it's a pretty even skew all the way up to the left, okay? All right, and then we have right skewed. Okay, what are the two variables being compared in this graph? Yearly income and relative frequency. Okay, so we see on the lower end of the yearly income, it's a lot more common for people to, and more frequent for people to be making in between $10,000 and $40,000, right? Now there is a slight little slope up from here because it's not as common to make, less than $5,000 a year unless you're doing like super part-time work. But for the most part, this is a pretty good indication that the more and more money you make, the less and less people there are making that money. I said it backwards. Well, no, not really. There's less people making a lot more money. Does that make sense? Yeah. That's pretty self-explanatory, right? There's not a whole lot of Jeff Bezos is making $4 billion a day or whatever it is. There's a lot of people like, me and other people that are making whatever this would be, this amount. Does that kind of help you see the difference between like what these three distributions are? Yeah? Sure. I appreciate the enthusiasm.